coming up with the Cartesian coordinate system.
Ah, yes. That idea came to me while I was lying in bed, being far too lazy to get up. I saw a fly buzzing around on the ceiling. Instead of swatting it, I began to imagine I could pinpoint its exact position using two numbers. Just take a corner of the ceiling as a reference, and voila, you have coordinates. X and Y were born.
Yeah, I think most people would have just hit snoozed and dozed right back off, but hey, you reinvented geometry. Hey everyone, today we're going to be talking to a guy who quite literally put math on the map. You might know him as the I think therefore I am guy. It's of course René Descartes. Now, Descartes, a lot of people know him because he was sort of the guy who came up with almost the concept of the matrix in the 17th century. But you know, there's a lot more to him than that. He was a huge pioneer in analytical geometry. He made a lot of contributions to science, especially in optics and meteorology. He was also a philosopher, came up with a lot of concepts about how the structure of knowledge is, how you get to the truth. Now, the character I'm going to interview here is an AI deepfake, but the content isn't AI generated. It's mostly sourced from the Stanford Encyclopedia of Philosophy, although of course I did use ChatGPT to help write the script. Now, without that out of the way, here I bring you the legendary mathematical genius, René Descartes. All right, I'm here with René Descartes. Monsieur, thank you so much for joining.
Merci beaucoup, monsieur. It's a pleasure to be here.
All right, today I want to cover a few things here. First one is your philosophy, then your science, then your mathematics, because I think you contributed to a lot of really interesting things back in the 17th century, so Renaissance, pre-Renaissance time. So the first thing I want to ask you is, I know a lot of things, like the Earth goes around the sun, the Earth is around. Some things I know because I've seen them, some things I know because I can infer them, some things people have told me. So to you, what does the structure of knowledge look like, and how do you get to the truth? I mean, is the structure is it like a tree of knowledge? Is it a web? Is it how does it look? What is it like?
To answer that, we must explore how we arrive at truth. We have intuition and deduction. By intuit, I refer to the conception of a clear and attentive mind, and not the fallible means of the senses or imagination. There are, you see, natures that are absolutely clear, such as that 3 + 1 = 4. This is intuition. After we intuit something, we have deduction, whereby we build upon these intuitive facts. This is necessary because there are facts which are not self-evident, but known with certainty, provided they are inferred from true and known principles through a continuous and uninterrupted sequence of reason. So, picture it as a chain of knowledge, propositions linked to each other, starting with the intuitive.
Okay, now this sounds a bit like the ideas in, at least to me, it reminds me of the ideas in Daniel Kahneman's book, like Thinking Fast and Slow. Yeah, it's hard to get on the blur, but so he says that there's system 1 and system 2 thinking, where system 1 is like, if I say bread and fill in the blank, then most English speakers would just immediately blurt out butter. You know, you didn't really think what are the best options to put in there. You sort of just know it. It's unconscious. It's snappy. And then there's system 2 thinking. So if I ask you what's 17 times 5, most people would be able to do that. But the thing is, it's very different from that first one, where here you have to really go through the steps. You have to be deliberate, you have to really think about it, and sort of exhaust your mental RAM. Unless you're some kind of John von Neumann or some other savant type, it really puts mental strain on you. So that's system 2. So the reason I bring that up is because if we take your intuition like system 1 and your deduction as system 2, then this could be just quirks of psychology. So how do we know that intuition is a source of truth, or why do you think that?
I reject that there is any connection between my intuition and some sort of fast, unconscious thinking. I contend that we have to distinguish between abstract logic, which is what I am talking about when I say that 2 + 2 = 4. We ought to distinguish that from our brains having memorized that as some kind of ingrained mantra. Someone who is not educated in math may not understand the meaning of the sentence 2 plus 2 equals 4, but he shall undoubtedly comprehend that 2 ears of corn and more 2 ears of corn will combine into one amount, which equals its constituent parts.
I mean, it would be nice if like a psychology experiment was done to test that. Although the closest thing I can think of is that in David Epstein's book Range, he talks about this experiment where some Soviet psychologists, when people are going from agrarian economies, or like from agriculture to industry, they went to the agrarians and started asking them some like IQ questions, mostly involving abstractions. So it would show them like a square made out of 4 lines, and then a square made out of dotted lines. And the whole point is the villagers were supposed to understand they're both a square. Like, it's the same concept, but they didn't get it because, like, for example, one said that the line square is a map and the dotted square is a watch. And, like, what does a map and a watch have to do to each other? Essentially, they didn't get the abstraction. And, well, the reason I bring that up is because, like, it shows that intuitions can a lot of times differ between people. So, like, is this really a source of truth in your opinion?
I don't think that such an experiment proves anything to my point. This is merely the recognition of shapes, which is a mental exercise that people who have never seen it will likely be bad at. Just as someone who has never learned math will be unable to calculate large sums. Pure reason does not depend on personal experience. It is logical and self-evident. I would still contend that these villagers would surely agree that something cannot be and not be at once.
Okay, you mentioned a chain of knowledge that starts at the most basic, like, axioms or pieces of knowledge. So what else can you say about this, like, chain structure?
Yeah, here I distinguish absolutes and relatives. Absolute natures being independent, causal, simple, universal, single, equal, similar, straight, and other such qualities.
Okay, so that's like the most basic concepts possible. Something like that something is or it has a length.
Exactly. Then relative natures share something with the absolute, but are more or less removed from it. Where we said that an absolute nature can be independent, a relative is dependent. Instead of a cause, it is an effect, not simple, but composite, particular rather than universal, not single, but many, not equal, but unequal, dissimilar as opposed to similar, oblique instead of straight, etc. Essentially, the relative natures are to some extent removed from the absolute. So, in our chain of knowledge, these relations should be distinguished, and the interconnections and their natural order should be noted.
Okay, so you mentioned this sort of like a foundation and then deduction-based structure. That would put you in the camp of rationalist philosophers. Those are the people who believe that you start off with basic, like, undeniable truths, and then you build on top of them. And that would put you in disagreement with someone like Locke, who was an empiricist. These are people who believe that you need to experience things and experiment especially in order to find out the truth, because they say that our intuitions and what we like think and come up with our brains isn't always attached to reality, as I'm sure we've seen examples of. So, like, this is interesting because it seems like your method is almost like a precursor or even like a variation of the scientific method in a way, which we know was codified by Sir Francis Bacon. And what I want to do here is sort of like put your method to a test or a challenge, because I want to see, like, let's take your method and see what you conclude from it versus what we have from the modern scientific method, and whether it like concurs with our modern experiments and our modern understanding. And the example I want to do is the rainbow, where you explain the colors of the rainbow in Meteorology 8. Please walk us through what you did and what you found out.
Well, firstly, one must notice that rainbows appear not only in the sky, but also in the air near us, whenever there are many drops of water in the air illuminated by the sun, as experience shows us in some fountains. To investigate this, I designed a sort of model droplet. You see, in my laboratory, I filled a perfectly round and transparent large flask with water, and I discovered that when the sun came from one section of the sky, and I looked from a certain angle, one part of the flask appeared completely red and incomparably more brilliant than the rest. That's the first color of the rainbow. So After some tinkering with the angle of the viewer and of the light, the colors began to divide into yellow and blue, and then the remaining colors of the primary rainbow. So decreasing one angle gave the primary rainbow's colors, and increasing another produced the secondaries. Later, I discovered that the light was being curved, that is refracted, in the flask. So here is where I used the intuition that I described in my method. You see, my method requires that every phenomenon in nature be reducible to the material, simple natures of extension, shape, and motion. We must determine what sort of mixture of simple natures is necessary for producing the rainbow. That is how the extension, shape, and motion of the particles of light produce the precise order of the colors. In my optics, I described light as the action or movement of particles, which must be pictured as small balls rolling in the pores of earthly bodies. When these balls are refracted by a common surface, all the refractions which occur on the same side of the balls cause them to turn in the same direction, but they do not necessarily have the same tendency to rotational speed. Particles of light can acquire different tendencies to rotational speed after refraction, depending on the bodies that surround them, so that those which have a much stronger tendency to rotate cause the color red, and those which have only a slightly stronger tendency cause yellow. Meanwhile, the nature of those that are visible at another point consist only in the fact that these small particles do not rotate as quickly as they usually do, so that green appears when they turn just a little more slowly, and blue where they turn very much more slowly. So, the deduction is as follows. Rainbows only appear with water droplets, irrespective of their size. What causes the two regions of color? Reflection and refraction. What causes the color? It is restricted light and refraction. To answer why for both of these questions, we intuit the nature of light and how it passes through media. We find that all parallel light rays converge into two streams after two refractions and one or two reflections, emerging from the drop in two regions. Meanwhile, color can only be difference in the tendency to rotate, produce, in passing one medium to another in refraction. Thus, that is how parallel light rays produce two distinct regions of color on a ball, causing the colors of the primary and secondary rainbows.
Okay, so we have sort of like a little branched tree of deduction going on here. I'll go ahead and reveal the truth. Your approach was spot on right up until you intuited the nature of light as like these spinning little balls of little particles. That's not correct. We know now that the nature of light is more like a wave, and like specifically Isaac Newton discovered that white light is composed of different colors, each with a different refractive index, and that dispersion is what causes the colors to separate. Like what we have is we have observation, and then we can make theories and explanations from those observations and see which ones model reality the closest.
Our ability to reason is the best we have. It's the only thing that could unite the rainbow theories of a colorblind person and a normally sighted one. This is a case where relying only on observations would cause problems.
Okay, I see what you mean there, although, and again, it's not really like a debate as to which one is right or wrong, but I think that the work you did here was very laudable, and I do want to continue with an area where pure intuition and deduction are used, and that's mathematics, because of course math is essentially like a closed theoretical system. So I want to take a look especially at your analytical geometry, because I think that the combination of algebra with geometry was one of the most revolutionary concepts or like paradigm shifts that ever happened in mathematics. And it looks like one of your main contributions here as well was the Cartesian coordinate system. So most of this was published in La Géométrie, but before we actually go into your contributions and your actual work itself, could you tell us like what was the state of geometry and algebra back in the 17th century?
Mathematicians were occupied with questions about what was and was not permitted in the conduct of geometry. In 1588, Comandino translated Pappus's collection into Latin. In this work, Pappus was making the case for how geometric problems ought to be solved, especially as they pertain to the construction of curves.
Okay, and just to provide some context here, Pappus of Alexandria, he was a Greek mathematician from the 4th century, and he wrote the collection circa 340 CE. And this covered like geometry, mechanics, some astronomy. Now, of course, Euclid's Elements was still a foundational text, but Pappus's collection is going to be more relevant to the combination of algebra and geometry, as we're going to see.
Yes, you see, Pappus classified geometric problems based on the construction of the curves necessary for their solution. If the problem is solved by a curve made by straight edge and compass, it is planar. If a problem is solved by a curve constructible by conic section, it is solid. And if a problem is solved by a curve that requires a more complicated construction, such as a conic or a spiral, it is line-like. However, there was considerable ambiguity in Pappus's text about whether the solid and line-like problems were at all solvable by geometric methods.
Okay, so basically you were asking, or like mathematicians were asking, that if a problem can't be solved with just a straight edge and compass, like is this even in the realm of geometry?
Yes, Pappus did not give us any verdict as to whether entities such as conics or so-called more complicated curves met the rigorous standards of geometrical construction. He reported the usefulness of these curves for the synthesis proofs, but also criticized the definitions of the curves. I recall him mentioning that there is a petitio principii, a circular reasoning, in the very definition of the curve. So it was a matter of great ambiguity over whether these were acceptable in geometry. Now, moving forwards, many mathematicians began to focus their efforts on this, especially regarding constructions such as the spiral and quadratrix.
Okay, so a quadratics curve, also called Hippias's quadratics, it's a type of curve that looks something like this. I should have it on the screen. And Dinostrus proved in 335 BCE that it could be used to square a circle, although the problem was that like this could not be done with just a straight edge and compass. You couldn't draw it with just those tools.
Correct. In 1589 and 1604, Christoph Clavius discussed the status of the quadratrix. He actually accepted the objections of Pappus, but supplied his own truly geometrical construction of the curve. But alas, this construction also could not be done with only a straight edge and compass. In his Supplement of Geometry, in 1593, François Viette investigated these controversies. He claimed that some of these problems could be solved properly geometrically with the Neusis problem. You see, what he did is he accepted as a postulate, an assumption, that the Neusis could be constructed, and that when we accept that, we can solve certain difficult problems such as trisecting a given angle, which cannot be done by only straight edge and compass. The problem, of course, is that because the Neusis cannot be constructed by straight edge and compass, there was still the open question of whether this was actually geometry. And in fact, neither the spiral nor the quadratrix we have mentioned can be solved via Neusis.
All right, and for some further clarification here, Neusis is a hendecagon, so that's an 11-gon, 11 sides, 11 angles, and as you pointed out, like it can't be constructed with just a straight edge and compass, so we're still dealing with like, is this still in the realm of geometry?
Yes, and I shall also comment on the use of algebra in the realm of geometrical problems. For Viette had managed, by adopting his Neusis postulate, to link geometrical construction with algebraic analysis. In 1591, in his Isagoge, he introduced a notation that allowed him to treat magnitudes in a general way. He used literal symbols to represent magnitudes generally without specifying whether they are arithmetical magnitudes, like numbers, or geometrical magnitudes, such as line segments or angles. He could thus represent arithmetic operations as applied to magnitudes in general. Essentially, if one encountered A plus B, they did not know whether this entailed adding two numbers on connecting two line segments. Now, he did use the Neusis to construct curves that satisfy cubic equations, with the roots, of course, being on the constructed curves. So, to solve a problem, such as identifying magnitudes that are proportional to two other magnitudes, he would rewrite the equations into standard form cubic equations.
Okay, so we have two lines, and if we want to get numbers that are proportional to both, we rewrite it into a cubic equation and construct a curve which will contain them. The thing is, though, that constructing this curve still couldn't be done with just a straight edge and compass. So yeah, that's the state of geometry at the time. Now, so I think it's important to get that out of the way, because it's going to be important to see like how that transitioned into analytical geometry that Descartes introduced. A lot of it boils down to the fact that in the 17th century, there were so many problems in geometry which involved these complex constructs like Neusis, quadratices, I believe that's plural, so many others that couldn't be drawn with just a straight edge and compass. Now, Viet and other mathematicians were seriously questioning whether these constructs were even geometric. So, like, what was your stance on them personally?
Well, recall how Pappus defined them. We have the aforementioned planar problems that are solvable by straight edge and compass, then solid problems by conics, and line-like problems by more complicated curves. But I propose that as with imaginary numbers, where we have problems that can be imagined but not solved, so too in geometry there is a class of problems that requires curves that are certainly only imaginary, such as the quadratrix. However, what I also proposed is that we can introduce new types of compasses which are no less exact and geometrical to draw certain curves. I applied some of these new compasses to problems as dividing a given angle into any number of equal parts, or constructing the roots of cubic equations and describing conic sections.
Yeah, and especially with the bisecting and trisecting and ensecting an angle, we know you can easily bisect an angle with a straight edge and compass, but you can't go further than that with just those tools. You can't ensect it or trisect it. So, like, the question here is, how did you manage to do that?
Well, for this task in particular, I had a compass with 4 rulers, 4 rods, and some pairwise hinges, which was able to draw a specific type of curve around an angle. Then, with this curve, the angle can be trisected with some basic straight lines and circles. This can even be generalized to divide into 4, 5, or even more equal parts. I used other compasses for different tasks. As it pertains the construction of mean proportionals that we have discussed, where Viet used his Neusis constructions, I instead used another instrument, a Mesolabe compass. This was in Book 3 of La Géométrie. I used this compass rather than the Neusis construction to draw a curve that provides the roots of the standard form cubic equations.
Okay, so it's basically the same process that Viet used in the sense that he rewrote the equation and then used a geometric curve to find the roots. But in your case, you used your famous Mesolabe compass to draw that curve rather than constructing it via Neusis like Viet did. And as you referenced it, your main work in geometry is the aptly named La Géométrie from 1637. Further solidified the link between algebra and geometry, and of course built on Viet's work. Now, I believe Book 1 is where you described how algebraic problems can be done geometrically. Actually, no, how geometric problems can be done algebraically, using algebra to solve geometric problems. So, can you help explain to us how this worked and how you did it?
Yes. You see, I relied on an interpretation of arithmetical operations, according to which these operations are taken to be closed operations on line segments. Traditionally, for instance, the product of 2 segments a times b was interpreted as a rectangle, but I instead interpreted the result as a new segment. So that allowed me to translate geometrical problems into equations. I also used a new exponential notation where I write the exponent as a superscript rather than saying squared or cubed. Thus, with these at my disposal, if we wish to solve any problem, we first suppose the solution already effected, and give names to all the lines that seem needful for its construction, both known and unknown. Then the task is to reduce the problem to an equation that expresses the unknown quantity or quantities in terms of the known quantities.
All right, yes, and in modern terms, so we would just call that rewriting the problem as a polynomial with 2 unknowns. Now, in Book 1 specifically, you gave a solution to the Pappus problem, which it's what's called a locus problem. So the solution is going to be some kind of set of points or a line or a curve that satisfies the conditions of the problem. In this case, it's called the Pappus curve, the solution. In the Pappus problem, we begin with a given number of lines, a given number of angles, a ratio, and a segment, and the task is to identify a curve where all the points on the curve satisfy a certain relation. And I think we can actually show this here. This is only going to be possible for the people watching. You see, we have these 2 lines. This is the 2-line version of the problem. Then we have this point P, and we connect it to the lines with these 2 angles. The problem is to find all such points P where the ratio between D1 and D2 stays the same. So for this simple 2-line version, you just move the P in a straight line towards L1. Now, Pappus in the collection gave a solution for the 3 and 4 line version of the problem. When you add more lines, since you have more of the distances, the ratio is d1 squared to d2 times d3. Or for 4 lines, it's the ratio of d1 times d2 to d3 times d4, so on. It might seem like a random problem to solve, but this is actually the problem that was perfect for applying geometry in an algebraic problem. So you provided a general solution for like any number of lines. Could you go over that?
Yes, this is the problem that for me truly necessitated the connection between algebra and geometry. Previous mathematicians, including Pappus himself, solved it for specific cases. Pappus for the 3 and 4 lines, and Apollonius gave a solution for 6 lines, where he used his theory of conics and the transformation of areas. I arrived at the general n-line solution by considering the problem from a different perspective, on which was more related to Viet's emerging use of algebra in geometry. Thus, one may represent geometric relationships using algebraic equations, rather than relying only on compass and straight-edge constructions. Also, rather than relying on conic sections for higher case solutions, I showed that the use of higher-degree algebraic curves based on equations could allow for a general solution. In Book 1, I applied my geometrical analysis to the 4-line case of the Pappus problem. I designate 2 given line segments, AB and BC, as coordinates x and y, such that all other lines needed to solve the problem will be expressed in terms of x and y. So we can derive an algebraic expression of the sought-after point C in terms of the 2 unknowns, x and y, and the given ratio z. To determine the point C, we need only one condition, that the product of a certain number of lines shall be equal to, or shall bear a given ratio to the product of certain other lines, as you have stated in the solution requirements. If a problem can be reduced to a single equation of degree not higher than 6, in which the unknown quantity or quantities are expressed in terms of a known quantity, then the roots of the equation can be constructed by straight edge and circle, or by conic, or by a more complicated curve that does not have degree higher than 4.
Right, so the curve that includes the sought-after point C can be pointwise constructed by using a ruler and compass to solve for the roots of a second-degree equation in 2 unknowns. That was a pivotal moment in geometry and algebra because it solidified the link between the two. And I think most people learn this in like high school math or maybe first year of college. I think that's enough for the math in this episode. Monsieur Descartes, it's been a pleasure having you here. We really appreciate all of your insights into philosophy, into mathematics, into science. I think that, I believe your nickname is the father of modern philosophy. I think it's fairly well deserved. You've made great contributions, and it's been a pleasure having the discussion with you, and I hope to have you on sometime in the future.
Indeed. Thank you for having me, Karim. Au revoir.